let's look at some forces on charges from magnetic fields. Instead of electric fields, now we're talking about magnetic fields. Okay, so we're going to assume we have some sort of a uniform magnetic field here. That's what the B's are. And remember, the X means it's like the tail of an arrow that's going in. So the B's is going straight in, and it's a uniform field, so it's just all going down into the paper, kind of a field. All right. And so we have two charges, positive one and a negative one. They each have a velocity. And so remember, the equation is, well, in general, we say QV cross B, where this is just the cross product reminding us that we use the right-hand rule to get the direction. We can say, for calculating, we'll do QVB sine theta. Okay? And so theta is angle where we start at velocity V, whatever the first, we start at V and go to B. So for both of these, the velocity is going straight to the side, to the right, and B is down. Right? So V to B, we're going down 90 degrees. And so in this case, theta is negative 90 degrees, or mostly we're just interested in the magnitude of the angle because we're going to use the right-hand rule to get the direction of the force. Okay, so magnitude-wise, theta is 90 degrees, and so sine of 90, remember sine starts at 0, goes up, its maximum is at 90, which is 1, right? And so size-wise, the force is going to be just QVB. But I'm getting ahead of myself here. So part A says, draw the paths of the charges in the B field. So, like I was saying, cross product tells us use the right-hand rule. We're going to do V, right? So put our whole hand kind of in the direction of the first thing, which is the V, cross B. And so we're going to bend our fingers down to go in the direction of B. So V, maybe leave one finger going in the V direction. B is down. And then the thumb, if you get everything 90 degrees, all these have to be at 90 degrees. So the thumb then tells us the direction of the force. The answer is the thumb. And so if we're looking at this positive charge here, the force is up, right? And so it's moving along. It has to be moving, right? Otherwise, the velocity is 0 and we get no force. So it has to be moving, have some velocity. So it's going to have some momentum. It's going to keep moving in this direction, but it's going to have a force and acceleration up like this, so it's going to actually end up moving maybe something like this and end up here, right? And so now its velocity is, say, like this, because it got turned by that force that was pushing straight up, right? And now if we have a V this way, across B, going straight down, now the force is this way. Trying to make it perpendicular. New force here. So what's going to happen is that's going to keep happening, and my paper's not big enough, but let's pretend like it's big enough, and it's going to, every time it gets the push this way, it goes that way, and so it's going to keep getting a force pushing perpendicular to where it's going, and it's just going to, the force is just going to keep pushing in, the velocity keeps going this way, getting turned, and so it's just going to make a big circle, or some sort of a circle. All right? Let's look at what happens to the negative charge. Negative charge has a velocity. Also, we could use a left-hand rule for negative charge, or what I like to do is just use the right-hand rule. So we're always using our right hand, and then whatever answer we get, take the negative of it. Take the opposite direction. All right, so again, same thing. We got V, right? Whole hand, whole fingers going V. Then the 3 fingers bend to go in the direction of B. Force would say up if it was positive, but we're negative, so force is the opposite direction. So the force is down on this one. All right. And so what's going to happen? It's going to move. It's moving this way, but then get some push this way. Running into each other. But so now it has, say, a velocity turned a little bit like this. All right, can't see that color. So the velocity was straight sideways, but we had a force straight down, so maybe now the velocity is this way. Right, it's moved maybe to this position. And then now what's the direction of the force? We got V like this, cross B going down. It says the force should go like this, but no, it's a negative negative charge, so the force is like this, right? And so same kind of thing's going to happen. It's every time it moves, it's going to get a force that points in towards the center of a circle, and it's going to just go around in a circle in the opposite direction, but still making a circle, right? Okay, and so we've got our paths for the positive and negative charges in this B field. So notice that this is for if the velocity is totally flat in the paper. If it had a little bit, if it was going a little bit up and straight that way, it'd make like a spiral and come up. It still makes circle shapes, if this was X and Y, still makes circle shapes, but it would go up, or if it had a little bit of a down velocity, it would go down, right? And so, anyway, but it would still make circles. Okay, so now we're going to look at just the positive charge. Say it's 2 microcoulombs. We have the B field, we'll say it's 200 milliteslas strong. We'll say the velocity is, I don't know, I guess let's call that 20 meters per second. And we want to know what is the force. All right, so we'll start on part B here. So B, force, is QVB sine theta. We already said V is this way, B is straight down, so sine theta becomes just 1. So we just want QVB. V, maybe we should make it like a cursive V to be like a velocity, not a capital V like volume or anything. And so we've got Q, 2 microcoulombs, micros 10 to the negative 6. Let's get everything in nice standard units. Velocity, 20 meters per second, good units there. And B is in milliteslas, so we'll say 0.200 teslas to get it into teslas, the standard unit. So the force will be in newtons then. We got everything in its good units, so 2e negative 6 times 20 times 0.2. Oh, lots of 2's in this problem. Okay. So we get 8 times 10 to the negative 6 newtons, or the force is 8 micronewtons. All right. We're assuming these are tiny things, tiny forces. Okay. So that is B. And then C says, what is the radius of the path if the mass is 10 to the negative 10 kilograms? Radius of what path? Then down here it's going to give us a different mass. So let's just say this is, let's just change what it says here a little bit. Let's make this the minus charge, and let's say this one path of positive charge. We're talking there. Okay. Or maybe we were just saying, oh, maybe that's what I was trying to do. Just have them both be the positive charge. But one positive charge with mass is this, and a different positive charge. Same charge, but different mass. Same charge on a different size particle. That's what it's looking for. Okay. Well, first off, let's start with C. And so if we have a force, right, to make it go in a circle, well, for Newton, we have ma, force equals ma. But then we know for a circle, for the acceleration, for centripetal acceleration, we call it a sub r, a sub s, or a sub c. We'll call it a sub r is v squared over r. Right? So to make something go in a circle, we need an acceleration towards the center of the circle in direction, and magnitude is v squared, where v is the tangential velocity. V is v squared over r, the radius of the circle. Okay, so if we're going to do this, we're going to say QVB, so MA equals M times v squared over r, and that's equal to this QVB we just had. Was this magnetic field is going to make the force that makes it go in a circle, so that's QVB. Anyway, so we can rearrange this and get R, and this is on your equation sheet. On your equation sheet, R is mv over qb, right? So we can just mv over qb, but this is where it comes from. Just rearrange that and you'll get it. Okay, and so we want the radius for m being 10 to the negative 10, so 10 to the negative 10 kilograms, yes, for standard unit, that's good. V was 20 meters per second. Q was 2 microcoulombs, 2 10 to the negative 6 coulombs. And B was 0.2 Tesla. All right, let's just do that. So we got 1e negative 10 times 20 divided by, in parentheses, 2e negative 6 times 0.2. We get 5 times 10 to the negative 3. 5 times 10 to the negative 3 meters. Since everything is in standard units, we get meters, or we could say 5 millimeters for R1, I guess we'll call it. I'm running out of room here. Okay, for part D, it says, what is the new radius if the particle actually has a mass of, so 10 to the negative 9, so it's a bigger particle. So for D, what if m equals 10 to the negative 9 kilograms? Then what happens? Well, it's kind of easy to see, hopefully. Only thing that changes is m, so we got 10 to the negative 9 kilograms, 20 meters per kilograms, 20 meters per second, divided by the same charge, we're assuming same charge, and 0.2 Tesla, same field. And so basically we've just, to get from, the only thing that's different is 10 to the negative 10, 10 to the negative 9, so this one is 10 times bigger, so this will be 5 times 10 to the negative 2 meters, or 5 centimeters. R2, I'll call it, I guess. Which hopefully that makes sense. So this is how mass spectrometers work. It's heavier things, hopefully it makes sense. Heavier things, if everything's moving the same speed, much particles shot out at the same speed, the heavier things will be harder to turn, right? When we do F equals ma, I had that somewhere, F equals ma, if they got a heavier mass, they'll get less acceleration, and so they won't turn as fast. They'll have a bigger radius of their circle, right? So the heavy thing is the bottom one here, has a radius of 5 centimeters, whereas the lighter thing had a radius of 5 millimeters, right? So one's going in a circle like this, and one's going in a tiny little circle, okay? And so, all right, so that's good for that problem. Problem 2. So this was force due to a moving charge, or a particle with charge on it that's moving. Okay. This one, now we're going to start talking about, we also feel forces on wires or some sort of conducting thing that has a current, right? Remember current, what is current? It's moving charge, a flow of charge. And so if charges are moving, right, then we have moving charges are going to feel a force in the field. So this wire, or whatever the conductor is going to feel a force because the current is moving charges, right? And so the version of the equation there is IL cross B, or just we can do ILB sine theta. And again, the direction, we're going to do I cross B now. All right, so we're going to find the direction of the force on the green wire. So here's our green wire. The direction is now like we were doing before with the V. Let me get my hand going here. So the direction, I is going down. B, let's see. I is going down. And B, oh my, I is going this way. B is going that way. So the force is coming out of the paper. Remember, we draw a force or vectors coming out as like the tip of an arrow or the tip of a pencil is just a little dot, right? So the force is coming out. So remember, down cross B is up. Down cross B is up. Okay. Whew, that was hard. Okay. Now we need to know how much I is what, to give a 0.5 Newton force if B is half a Tesla and the wire is 2 meters long. Okay, so we're going to use F is IL B sine theta. In this case, we got L going this way and B going, L is down. All right, we got a length of wire here, some L, and the current is going down. So the direction, IL, the direction we're talking about is down because the current's going down. And B is this way. So we're going here to here is our theta, which is 90 degrees. And so working on B here, so theta is 90 degrees, and so the force is ILB sine 90. Sine 90 is 1, so it's just ILB. Is what we're looking for. So we want ILB to be equal to F. And so if we want to know what I is, rearrange this for I is going to be F divided by LB. So I is F. We want half a Newton force. We had L, 2 meter long wire. And the B field, we said, was half a Tesla in magnitude. That's all we're dealing with here. So we got half and a half, and then that makes 1 over 2 be a half. Oh boy, we got lots of halves. So 0.5 amps is the current we would need. Okay, pretty reasonable. Got lucky with my numbers on that one. I think I did everything right. Okay. So that was B. On C, what is the direction of the force on the blue wire? All right, see if I can get my hand to do this. We got the blue wire, current's going this way. And then we've got the B field going that way. So again, the force is still straight up. All right, so the force on this wire is also straight up. Because really what matters is how B and I are related to each other in terms of B and I making a plane with each other. So you go from I to B, you're making a plane this way, and the force is going to be perpendicular to that plane. Okay, so the force is also straight up. Okay, so then we already did C. And then D, what is the current to give a half a Newton force with the same B, same L? Okay. Now, what is theta for this one? So theta, the current is going this way, right? And then the angle to get to B, I've written here, is 110 degrees, just making up numbers. But to go from going this way to go that way, you got to go 100 degrees clockwise, so it's or counterclockwise, so it's positive. So theta equals 110 degrees. And so now the force is ILB sine 110. Oh, okay, and we were wanting to know I again, so solve for I. So I is going to be F divided by LB sine 110 degrees. All right, are we getting close to being done? I think I'll have room. All right, so I is F, which was a half a Newton, L 2 meters, B half a Tesla, and sine 110 degrees. 0.5 divided by, put a bunch of stuff in parentheses here, 2 times a half, probably didn't have to do that, times sine of 110. Divided like it should, looks good. Looks like 0.532 amps. Okay, so does that make sense? We need more current. Can we see this? We need more current. Why do we need more current? Because it's not straight lined up, right? If to get the maximum force, we would be perpendicular to get the 90 degrees, but we're off a little bit. We're turned a little bit, so we're not getting the max force we could for the current that we're doing, so we have to put in more current, right? To get up to the same amount of force that we had when we were perpendicular, lined up just right, we only need half an amp. To be off a little bit makes us need a little more than half an amp. Okay. E. Write an equation to get the force per meter. Okay, so say we wanted, here we just use a length of wire, 2 meters. Let's say we had a really long wire, like a power line or something, and we didn't want to know for the whole huge long wire. We just want to know in this area, what is the force per meter? All right, so we're just going to rearrange, look at our force equations. So force is ILB sine theta. L is the length, right? Is how long the line is. So we can rearrange this and do force, just divide both sides by L to get the force per meter, force per length, and that's just going to be IB sine theta. All right, so this equals the force per meter. So some problems might give you that you want a certain force per meter, or they might give you the force per meter and have you find something else. And so force per meter is just F over L. So, and you can find what they're looking for then if you're given one or the other that way. Okay, so that is E. So we'll go ahead and stop there.